down into groups of about 3 or 4. Split up, go around, take measurements, do your discussions. You will not finish today, but we'll come back. You come back tomorrow?
Yeah, tomorrow.
Okay, well, when you come back, I'll give you time to finish up. I'll finish talking about the physics topics here, talk a little bit more about the scenes, and then each group will have an opportunity to talk about how they solved the crime, maybe some of the steps they took, some problems they had thinking about it, maybe they went into some dead ends and so forth. Okay? Okay. So, since I gave this presentation to a wide range of teachers from elementary school through high school physics teachers, I had to cover a wide range of material. I'm going to very quickly go through measurements and units because this is something that you're all very familiar with, I'm sure. And it'll just be a quick review. That is, we're going to be using the SI units, right? We use this in science all the time. The meters, the kilograms, and the seconds. We won't even cover joules and watts. We'll talk about force tomorrow when we start talking about Newton's laws of motion. I'm going to ask you to do some unit conversions here for measurements because obviously I had to put a scale model here of the hotel. I couldn't bring in a whole hotel, so you're going to take some measurements and I'm going to tell you what the scale is. Okay. So just to kind of get you in the calculational mode, you might want to get out a piece of paper, right, and a pencil, a calculator. All right, everyone bring their own calculator? Okay. You don't have to remember any conversions. Everything you need, I will give to you in order to solve the crime. Okay, everything you need, I'll give to you. But just to get you in the physics mode, you haven't had any physics yet, right?
Back to that last slide.
The last slide?
Yeah.
This slide?
Yeah, just 1 second.
Okay. Okay, so, we have, I think Evelyn, our Temple student, might have been going a little fast, over the bridge. She might have been going it was probably a 40-mile-an-hour bridge, and she was going 65 miles an hour. Let me ask you, can you take that 65 miles per hour and convert it for me? I want you to convert it into feet per second. Now, forget that one for feet per second. Now, here are the conversion factors. So what would you come up with if you do that? I'm hearing some good answers. Feet per second. No, I'm asking you to go to feet per second.
Okay, I'll go straight to meters. I'm 29. I'm standing.
You're going too fast for me. Okay, so basically what I like to do is be sure my units are going to cancel, so I just simply go 65 miles per hour, right? And so if let's say I want to get rid of the miles, where would I put it?
1 mile on the bottom.
1 mile at the bottom, and what do I put at the top?
5,000.
Okay, that's good, because that way I can cancel my miles, right? And now I want to go from hours to seconds, and I'm feeling fairly confident, so I'll just keep going. I'll just say times. So where does the hour go? Numerator? Numerator, okay. So I can cancel that. And what's at the bottom? 3,600 seconds. Okay. And that gives me feet per second. If I do that calculation, I got, I think, approximately 95.
95.3.
Okay, let me round it, all right? 95 feet per second. That's good. Okay. Now, what's the next step? I want to take this and go meters per second. What would I do?
Divide by
3.281.
Feet per second. I like to multiply. So multiply. Where do I put the feet? At the bottom. What do I put at the top? The meters? Okay, and what conversion did I give you?
3.281.
So 1 meter is the 3.281. Okay, and I think that's about 29. Is that what you get? Okay, good. 29 meters per second. Okay. This is, I don't know, this is kind of the way I like to do it, because that way I can be sure I cancel my units. Is that what you do with your students, or? Yeah. You try, yes. I try. Okay. I feel more confident when I can see things out step by step. All right. Well, that's very good. So let's just jump into this crime scene here. We're going to be talking about muzzle velocities. Let me ask you this: anyone here shoot? You shoot like pistol shooting, target shooting? Okay. Yeah. I wasn't sure. What the muzzle velocity of. It's a wide range, obviously, depending on the type of firearm you use. But this is accurate in the sense that it's roughly, it could be about this. So the muzzle speed of a bullet is 400 meters per second. So I said, well, I have a hard time thinking, how fast is that, 400 meters per second? So what is that in miles per hour? Can you give me that in miles per hour? Do you have it? Anyone get 1,500? That's good, because that's wrong. Right. 400 meters per second, and that was 1,607 meters per mile, and 3,600 seconds per hour. And I got approximately 895 miles per hour. Now that really impressed me when I first figured that out, because that tells me something, because that's like way faster than the speed of sound, right? 600-700 miles an hour. So I was impressed by how fast a bullet can move. Okay. So far so good? All right, great. Now, we're going to be working in 2 dimensions, right? The horizontal and the vertical dimension. And so I'll be talking about horizontal travel and vertical travel. And I might lapse into, instead of calling it horizontal, the X and the Y direction. Okay? And our equations that we're going to be using, and there are going to be 3 main equations we're going to use to solve these crimes. You don't have to know memorize the equations. I'm going to give them to you, but you have to know how to use them. Okay. All right. So the first equation, which you probably will know, you have my name, right? Good. We're going to talk about, I want to talk about speed and velocity. right? Speed, some people may use the words interchangeably, but to a physicist, they really mean two different things. So who teaches physics here? Okay, so you know that the difference is, you might say it's a scalar versus a vector, but we're not going to go into that today. Speed is just, how fast you're going, right? How much distance you travel over a period of time. So I drove from, do you know where Berwyn is?
Yes.
You don't? You know where Paoli is?
Yes.
You know where Philadelphia is?
Yes.
All right, that way? Okay. I live in I drove from Berwyn to Immaculata on Route 30. Do you know Route 30?
Yes.
All right. So I would say my average speed was 30 miles an hour. Okay. My average velocity, however, would have been 30 miles per hour west, because I needed, velocity includes the direction. Okay. So speed is a scalar, it's just a quantity, it's a magnitude. Velocity tells me something, not only my speed, but also which direction I'm going. Okay. Although I'm going to use the term velocity, and we're going to use the letter V for velocity, we're mostly going to be concerned with the magnitude, okay? Not the direction, pretty much. So let's just say velocity is equal to, and I'm going to use x for distance over time. All right? So the first important equation that you're going to use in solving the crime is this one here. Distance is velocity times time. Or you could say, distance is equal to velocity times time. I'm going to use x for distance. Now, people who teach who teaches physics again? What do you use for distance in your class?
I just usually use D.
D.
Could be D, could be X, depending on what direction.
Okay, yeah, it's
Y.
depending on what book you use. Someone told me they use P. I've seen S. So S. Yeah. So I'm going to use X. So everyone's okay with X, right? This equation is good when we have a constant velocity, right? It's not changing. So if I were to roll a ball on the floor in the X direction and I took a snapshot every second, it would look like this, right? It covers the same amount of distance in equal amounts of time, right? Velocity. We have no acceleration. Okay, so first important equation. So you could do this in your head. Calculate the distance you will travel if you maintain an average speed of 10 meters per second for 40 seconds. 400, right. 400, what's the units? Meters, good. Okay. However, okay, as you probably know, if you drive Route 30, you are not going at a constant velocity or a constant speed, all right? You're going to go a little bit, you come to a stoplight, right, Paul? And then you're going to accelerate, maybe between Berwyn and Paoli, I might go 40 miles an hour. Then when I hit Paoli, I better drop it down to 25 if I don't want to get a speeding ticket. Then I'm going to stop about 3 times in Paoli, right? So there's a lot of acceleration and deceleration throughout. Right. So in terms of physics, acceleration can mean one of two things. It can mean I've changed my speed. Right? I slowed down, I stopped, I picked up speed again, I accelerated. Or in physics, it means I changed my direction. One or the other, or both could be occurring. Now, it's easy to understand a change in speed because we intuitively, understand braking and slowing down or accelerating and speeding up. But in physics, I could have a situation such as I'm in my car and I'm going on a circular track and I am traveling at the same speed, 30 miles an hour, 30 miles an hour, 30 miles. So my speed is constant, but I'm continually changing my direction. I'm not going in a straight line. Okay? So I'm going around, right? And when I'm continually changing my direction, I am changing my acceleration, even though the speed is the same. I'm not going to worry too much about this in this class in solving the crime. When I talk about acceleration, I'm going to be talking about changing my speed. And the definition of acceleration is change of velocity with time. Okay. My second important equation, so this is my first one up here. My second one is going to be acceleration is equal to change in velocity with time, or the delta means a change, which is the same as final velocity minus initial over time. And in many cases, my initial velocity is going to be 0. So this will drop right out, make it very easy. Okay. So if I take that ball and I roll it on the floor again, but now, instead of having a constant velocity, I'm accelerating it, and I take a snapshot every second, it's going to cover greater distance as it continues to accelerate. Okay, looks like this. The units for velocity was meters per second. The units for acceleration, meters per second squared. Okay. Let's apply this. Easy problem. All right. A police car, when they hear about the accident over the Schuylkill, begins to accelerate from rest. They stopped at a donut shop, had a cup of coffee, right? Picks it up. Goes to 90 kilometers per hour. All right. Do you ever notice on my car, my speedometer is in miles per hour and kilometers per hour? Have you looked at your car? Yeah. You could switch it. In fact, it really blew me one time because I brought my car in for servicing, and they must have pushed the button by mistake, and I didn't know it. And all of a sudden, I'm in kilometers per hour. I'm going, what the heck? I'm going 80 miles. It really wasn't. I was going 80 kilometers per hour. When I pushed it, I went back down to 55 miles an hour. So it accelerates from 90 kilometers per hour from rest to that in 5 seconds. What is its acceleration in meters per second? This is a two-part problem. Why is it two-part? Yeah, the units. You gotta take care of the units first. Let's get all our units into meters per second. So, could you please convert for me 90 kilometers per hour to meters per second? Let's give him a second to do that. What'd you get? How many meters per second is that? Anyone want to share what speed he's really at in meters per second? Not the acceleration, the speed, just the speed.
25 meters.
Okay, so you take 90 kilometers per hour. How many meters in a kilometer? So I'll put the kilometers down here to cancel. 1,000 meters, that enables me to cancel there. I have 1 hour, 3,600 seconds. 25? Okay, that's his final speed. What's his initial speed? Okay, so I have V initial is 0, V final is 25 meters per second. My time is 5 seconds. And then I can calculate the acceleration. So acceleration is equal to V final minus V initial over the time. So that's 25 meters per second minus 0 over 5 seconds. Five meters per second squared. Everyone get that? Okay. Let me challenge you a little bit more on this before we go on to acceleration due to gravity. Any questions so far? Easy stuff, right? Okay. So here's a situation where an automobile is moving to the right along a highway when a police car pulls up behind. The driver puts on the brakes. If the initial velocity, just before he touches the brakes, is 15 meters per second, and it takes 5 seconds to slow to 5 meters per second, what was the car's average acceleration? You don't have any units to convert to, but can you tell me what the acceleration is? Down what I know. My initial velocity, 15 meters per second. My final velocity, 5 meters per second. The time was 5 seconds. The equation I'm going to use, all right, and then I substitute in my values, being careful to remember that my final velocity is smaller than my initial velocity, and that gave me a negative value. And the negative value meant I was slowing down. Okay, so far so good. All right, so we've been talking about acceleration in the x direction. In these crime problems, we're going to be working about acceleration. What happens when I let this go? Right, it accelerates due to gravity. Okay. Can I go to the next? Are you still looking at the slide? Okay. Whoops. Sorry. Okay, so the specific type of acceleration is acceleration due to the force of gravity. All right. So who's that? Sir Isaac Newton. Okay. So acceleration, free fall due to gravity. Objects accelerate as they fall. Okay. So we take the same equation here that we've used before, only now it's very specific. The force we're dealing with is gravity. It's very specific for Earth. The acceleration is always the same. We give it a special letter, g, and we know what it is, 9.8 meters per second squared. Okay, so acceleration, notice the units are correct, meters per second squared. So this equation here, or just rearranging it a little, is the same as this equation. So you don't have to memorize two. It's the same one, only A now is g. And we know what it is. It's 9.8 meters per second squared. All right. And who's this guy? Galileo, right. Okay. You knew by the hat. All right, so an apple falls freely from a tree and accelerates for 1.5 seconds. At what velocity will it hit Newton's head? All right, it's a little multiplication here. You have to multiply time times g. Yeah, it's about 14 something meters per second. All right, so all right. Velocity is equal to acceleration due to gravity times t, simple multiplication. Okay. So we know how fast at any particular time something, you're going to be given information about what the velocity of that guy was when he hit the ground. The medical examiner is going to tell you what his velocity was when he hit the ground. So that might help you solve your crime. Okay. How about this? The third equation, the third important one, is going to be this one here. Right? That is, how far does something fall over a period of time? Right? Free fall under acceleration due to gravity. And notice I'm using y because it's in the downward direction. So you can see that this ball is accelerating because every instant of time I take the snapshot, it's going further and further. Okay? And it's accelerating due to g. All right. How far, y, is equal to 1/2 gt squared. Don't forget to square it. Okay? So this is going to be your third important equation. One-half gt squared. So this I do for you. An apple falls freely from a tree. It hits Newton's head in 1.5 seconds. How far did the apple fall? We know how fast it was going. All right. 1.5 square it. Multiply times 9.8, take half of it, about 11 meters. So in 1.5 seconds, which is pretty fast, it drops like 30 plus feet. That's quite a bit, quite a distance it drops. So I think by the time it hits Newton in the head, it's going to be applesauce by hitting that far. Some of you may have seen this next problem. I don't remember. This skydiving dog problem? No, you were sleeping that night. A skydiving dog steps from a high-flying helicopter. In the absence of air resistance, how far has she fallen at the end of 12-second jump? So why do I say this? Friction, yeah, slowing them down. So anyone do skydiving here? No. I had one person so far that's done skydiving. You know, if you jump out of a plane, and let's say your parachute doesn't open, right? At some point, you're going to reach a velocity, what I want to call a terminal velocity. You're not going to go any faster because of air resistance. You continue to accelerate, 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 and then you get to a point where you're not going to go any faster. What is that speed? Does anyone know?
Terminal velocity.
What? Terminal velocity, what is it? What's its value?
Depends.
Yeah, absolutely. About what is its value? A human being, human body.
130 miles an hour.
Very good guess. Yeah, anywhere between, I guess, 110 and 150. So not to worry. You won't go any faster. It's that last second that kills you. Okay. Can you figure out this? What's the answer to this? 7 what?
7 and 5?
Very good. Did you get it, guys? It's about 700. I got 706 meters. 706 meters. All right, just 12 times 12 is 144. Take half of it and then multiply it by g. You could. You could take half a G and then multiply it. Doesn't make any difference. Okay, so you're going to use these three equations to solve these crimes, right? And just as a reminder, before I let you loose, whoops. Just as a reminder, you're going to find that you might be able to get some information regarding free fall. Like if you know how high something is, you can determine how long it's falling, and you might be able to use that in other equations, okay? Because the actions are independent, right? Going this way and coming down, you end up with projectile motion, but you might be able to use one equation to determine, for example, time, and then use it to find something else over here. Right? How far did he go from the hotel? Okay, I'm going to hand out the stories to you. You can start it. Get teams of about 3 or 4, please. Some will require some measurements, some do not. When we come back, when do we meet again?
Tomorrow.
When we come back tomorrow, I'll give you more time. I'll talk a little bit more. I'll give you more time to work on this, and then your teams can give a presentation about what you found and what problems you ran into or what dead ends maybe you ran into before you came around. Okay?